Is that still large enough? I've never been on TV before. So if you have trouble reading it or understanding, just let me know, okay? All right. Now, the depletion region, depletion charge, is equal to donor concentration. And this, I don't know where this comes from. Oh well, this comes from the Z book. Okay. Now this just says an equal but opposite charge is induced in the metal, right? That's all we're saying with this. We're taking the charge here due to the neutral level, surface state charge, adding it to the depletion charge, and we're saying the opposite charge has to be found in the metal, right? This QM equals minus QCC. Okay. Now, using Gauss's law, Gauss's law, right? We can derive an expression for the voltage drop across the thin oxide layer. Basically, we get, let's do the thickness of the oxide times the enclosed charge divided by materials tubing. Okay. From the energy diagram, you can also see that delta is equal to the metal work function minus the affinity minus the Schottky barrier height, right? Okay, if we equate these two equations and substitute into our charge balance, okay, we get okay. No. And now, of course, we're solving for the Schottky barrier height here and here. Does everybody know that Dr. Lester was going to be here today?
No.
No? Neither did the guy who's, I have a friend who's, Dr. Lester's supposed to give him his oral review board for his PhD defense. Thursday. So he was pretty shocked too. Okay, solving a bunch of math. And I'll tell you what this gamma S is in a second. These boards aren't quite long enough. Again, this Q is just to make the units all correct. Okay. Where gamma S is just this. And this Fm is equal to our max field, which is equal to, from the equation, 2Q ND BBI over permittivity. Okay. So there's a pretty ugly equation for you.
What is this, what Greek letter is? Would be OX, the substrate?
Oh, that's the oxide. Oh, it's right here. Oxide thickness.
Oh,
Sorry. I didn't draw that on the board, but excuse me. Okay. Now, we have a couple of thoughts for this. What happens if the oxide thickness goes to 0? Right? Then our gamma S would go to 1. Right? And we get our barrier height is simply equal to our metal work function minus our electron affinity, which is what we'd expect. That's an ideal case. And if our surface states, in sub s, right, gets very large, just go to infinity, right? Then from our equation over here, we can see that gamma s would go to 0. And so our work function, our barrier height, is simply be dependent on the band gap at our neutral level, which is kind of interesting. Okay. What this means is that our Schottky barrier height has no dependence on the Fermi level. Okay, this is called pinning. So the Fermi level is pinned. Pinned at the surface. The surface of the semiconductor. Okay. It won't matter? What? Metal? We put on the semiconductor. We get the same okay. What that means is, back over, please. What that simply means is right here, we've got so many surface states here, right? So many that if we try to move this Fermi level up or down a little bit by changing the metal, what happens is we uncover so many charges in all these surface states, you know, it'd be like trying to uncover an infinite amount of charge, right? It's too much work. The Fermi level is pinned where it's at. It's kind of like being, trying to describe it. It's like almost like a wall of charge, you know. If you're here at the wall, if you're not pushing on it at all, your hand stays here. But no matter how hard you push on it, your hand's still going to stay there. Because there's an infinite, well, there's not infinite, but there's such a large charge there pushing against a change in the Fermi level. I don't know if that describes, if I just confused everybody. There you go. Okay, let me see. I worked out a little problem here. I would be better prepared, but I had a water pipe break in the wall of my bathroom last night. So I was running around like a crazy man. So let's do this problem and discuss it some more. Oh, what did I just erase? Fermi level pinning. All right, hold on a second right here. Remember, surface states go to infinity. MS goes to 0. So Q, phi, Bn. They go to Q, band gap, minus neutral L. No dependence on IM, metal, work function. So therefore, no dependence on the metal. Depends solely on the Fermi level, the semiconductor. Yes?
In the last formula, yes.
Sorry, can you speak up?
In the last formula wrote, the band gap should be over Q. Yes.
Oh. Oh yeah, I got the Q, okay. Sorry. Thank you. Actually, I just need that, right? Instead of Q over here. All right, where was I? All right, I was going to do a problem. Everybody caught up? Am I going too fast?
Way too fast.
Y'all look very thrilled. Well, I'm going pretty fast, actually. This is supposed to be one lecture. What's the difference between the Titanic and President Clinton? Only 800 women went down on the Titanic. I don't know what that means. Okay. Can I erase this? Take that for a yes.